I'll launch into our first presentation. It's from Yury Gorbachev of Itseez. Yury is a principal engineer at Itseez, responsible for one of Itseez's primary products, the accelerated CV library. Yury's interests are in embedded vision platforms and automotive vision. And in this particular talk, he's going to explore some of the most common pitfalls of vision product development projects and present practical ways of avoiding them, drawn from examples of real-life product development and projects. So, Yury?
Okay. Thanks for the introduction. So basically, maybe what I could start with is to tell what Itseez is and why are we capable of talking about our experiences and talking about common pitfalls in the project and product development. First of all, we are a company that is in the computer vision market for more than 10 years. And this is actually the only thing that we are specializing in. So we are only doing computer vision related or computer vision based products. Not only we are doing our own products, we also help customers to do prototyping work. We help customers to do project implementation work in a computer vision area. So in a year we do, I don't know how many products and how many projects. So we basically, things that we are going to discuss here, we are passing more than multiple times in a year. And basically the reason for why we compiled this presentation is that we wanted to share the experience with you and to help you to avoid problems in the implementation of the projects. So things that we are going to cover briefly are here. So those are requirements, data, platform selection, and then hardware again, customer feedback, and maintenance of the products, or things that you should consider for maintenance. Those are briefly, we are now going to look at them in the details. So there was a presentation yesterday that basically showed similarities between game development and computer vision. And there was a recipe for a good computer vision project, let's put it like that, or how to make a good computer vision product. Basically, the recipe was of two bullets. I don't know if you have seen it, but first bullet is to get a bunch of PhDs, and second, start hacking using OpenCV. Basically, this is the key to success for most of the products, most of the innovative products. So there is no straightforward way to implement certain thing in a computer vision at the moment. And as a result, what happens is that you may have some ideas on how your product will be working, what your product will implement, and in which way. But this never ends up to be like that in the end. So either you face problems that you were not expected, or you have to modify the requirements and exclude some things that you wanted to support initially. This is happening because most of the computer vision work is still highly researched to a high extent. And reason why we are bringing this up is that basically all those missed requirements, or let's say too much attention to requirements, to keeping those requirements and to following strict project plan could potentially impact your project. So it can be either additional work that you haven't planned, or you could potentially have to reduce the scope of the project. So just to give an example, we have, as it was mentioned, we have ADAS product suite, and basically one of the products there is traffic sign recognition. And one of the requirements is traffic sign recognition for Europe. Basically, if you look 60, this is how the road sign look in Europe. This is the speed limit, more or less. And it looks pretty similar. You have a standard that describes size, and you have a standard that describes color, size of the text, and things like that. pretty easy to put this in the requirements, so you have no problems doing that. But then you go to actual testing, or you go to data collection or something like that, and then you see all those scenarios that basically you were not expected in, and then when you face them, you actually understand that you have to add additional functionality. So first example on the left is a sign on the back of the truck. So apparently people, the truckers in Europe, they tend to put speed limit signs on the back of the truck. So if you have a system that detects them, then most likely you are detecting them. And saying to your customer, saying to the consumer that basically there is a speed limit, and then other examples here as well. So my point here is that as soon as you get to actual real life scenarios, you probably will figure out some potentially new scenarios that you have to cope with. Then there is a lot of talking about deep learning and implementing things with the convolutional networks and so forth, but people tend to forget that any kind of machine learning algorithm, any kind of computer vision algorithm requires data. So if you are lucky, then you don't have to pre-process this data a lot. But in most of the cases, to have data suitable for machine learning, you have to first collect this data. Second, you have to pre-process it somehow. In some cases, just simply do annotation. And if possible, you have to do that with the target hardware as well. And then, only then, you are capable of starting writing certain algorithms. Training convolutional networks, for example, requires a lot of samples. So if you don't have them, then it's of no use for you. And then, if this is not planned, if you are just planning to start algorithm implementation, then probably you are already behind. So there is I don't know if you have been to a technical exhibit over there, but there is a company that allows you to do data annotation, that does data annotation instead of you. So that basically tells you that there is a substantial activity that somebody will do for you. And if you don't plan for that, if you don't consider this in the first place, then you are already behind your schedule. So again, example from ADAS. This is the statistics for traffic signs. So the graph on the left shows how many road signs are you able to capture if you're driving for 1 hour. So on the top, this is USA, and on the bottom green is the Germany. So apparently in USA, you are capable to capture, this is the actual statistics from our data set. Apparently, you are able to capture 24 road signs if you just drive for 1 hour in the US, 60 in Germany. So assuming you want to collect about like 1,000 signs for test data set to get the proper coverage, you need to drive, what is this, 40 hours pure driving in Europe and 16 hours in Germany just to collect this data. And this is not considering different road signs, so different types of road signs. This is not considering weather conditions, and this is not considering lighting situations like evening, morning, and things like that. And then you have to annotate them, and in some cases, annotation data can take even more. So if you don't consider this function, if you don't consider this activity in your project, then this can be a substantial impact on your schedule. Then platform selection. There is now a lot of talk and a lot of demos on compute platforms. Basically, GPUs, DSPs, and SIMD are most powerful ones. So now people are marketing FPGAs as well, and even more complicated platforms. And basically, you can go and select out of them in a freely manner, more or less. But the problem is that not all compute platforms fit all algorithms. So what happens is that in most of the project, the situation that we are facing in most of the project is that customers select hardware first by using some criteria, I don't know, about how many frames per second are those platforms capable of processing when they are showing some demo in, I don't know, technical exhibit. They bring hardware to us and say, now we want to make algorithm running on those. And it's not so easy for us to do that because more or less we are limited in algorithm implementation approaches. What this usually ends up in our cases and in other cases is that algorithm usually is suboptimal on a particular hardware. So either algorithm must be limited to certain hardware limitations, or it must support additional functionality, or it must implement it in a different way. Usually this is higher power consumption and unnecessary complication. So let us look at a simple example. So there are several types of SoCs which support a very high amount of vector units and very small amount of scalar code, scalar capability. So the idea is that apparently you can implement everything as a vectorizable code, and then basically you have a control code that is running on a scalar core, very low power scalar core that is sending control information to the vectorizing units, just compute this, compute that, and so forth. And the idea is that everything is vectorized again. However, assuming that you have, let's look at the following algorithm. So you have a key point search function that probably can be vectorized. Then you have external sensor that tells you on which particular part of the image you could look for objects. So that way you are able to identify regions of interest on that particular frame. Those are areas where you want to look for a particular object. So assuming you want to look for, like, I don't know, vehicles or pedestrians, things like that. So you identified certain suspicious area by key point, simple key point algorithm that goes through the whole frame. Then you use maybe some simple laser sensor or something like that that tells you that area is not empty. And then you want to actually look if there is a pedestrian or something like that. So you take a cascade approach, look through those regions of interest, and then you have identified, then you narrowed probably a list of the regions of interest to even smaller number. And then you have to do candidate analysis. And all those functions starting from here potentially have no benefit out of SIMD. So cascade can be optimized by factor of 2 or 3 using SIMD, which is very small number. And later candidate analysis, that could be potentially any kind of custom function that you implement. Maybe you're searching for head and arms and things like that. So those things are very hard to vectorize, and also they are not using consistent memory access and so forth. So in that particular case, if you assume the situation that you have a hardware pre-selected by your customer or by your hardware team, you are basically have to implement different algorithm more or less to have a more beneficial solution. And this is exactly the situation when you want to look at the hardware, look at the algorithm first, and then potentially select hardware. On the hardware, to build up on the hardware even more, so if there is a possibility to change the hardware for the purposes of your algorithm, then we would strongly recommend to do this. First of all, you are able to change the camera parameters and the other things. So, like, for example, there was a keynote in the morning about how NASA does things. So you've probably seen that they use different kind of tricks, stereo vision and other near infrared cameras and things like that. So this is exactly the case when you benefit out of using some custom hardware for your algorithm. This is exactly the case when you benefit out of changing hardware in favor of your algorithm. So not only this makes things easier, not only this makes things easier for your algorithm, some things only possible when you use specific imagers or things like that. So for example, you can use depth information along with the RGB, and that can make your life more easier, and that can allow you to avoid certain problems with the algorithms. IMUs is another example. So IMUs can be used for like visual odometry and all those kind of things. IMUs can be used to estimate the motion speed and so forth. So that kind of information can be precious when you implement certain things like structure from motion and so forth. Also, in some of the cases, it might be that you don't need to do a lot of processing on the device itself. If latency requirements allow you to do processing in the cloud, maybe this is what you should consider instead. Just sending some data to the cloud, processing it with whatever deep learning fancy stuff that was done there, and then send it back. So instead of selecting the most powerful SoC. So just an example of what I mentioned. So this is the staircase detection, pretty frequent algorithm for robotics, for robots that are driving around and maybe helping people and so forth. So on the left here, this is the depth information for the staircase, and on the right, those are two examples of RGB, plain RGB images. So this looks like a staircase, and this looks as a staircase to certain algorithms. So if you don't properly design your algorithm, then you're probably failing quite a lot on those kind of things. This kind of image allows you to do much more simpler processing comparing to RGB. So if you're capable of changing your hardware to assist your algorithm, then this is exactly the case when you should do that. Not only because this is easier, it is also here more maintainable, and then this is also less power greedy, so to say. So building up on all those things that I've mentioned, what we recommend to do, especially for complicated and innovative products and that you want to go over. First of all, we recommend to do initial snapshot of the requirements, where you want to specify things that you want to detect, things that you want to work with, conditions that you work in, like is it indoor, outdoor, I don't know, night conditions, day conditions, weather conditions, so forth. Then you do initial algorithm design. Basically, this is the proof of concept. So you get some initial prototype and you get the prototype results. Those prototype results can give you two hints. First of all, based on those results, you can update your requirements. You can update your project scope. You can update things that you want to support and things that you don't want to support. Most likely, over here, somewhere in the beginning, you will go and do data collection. You will go and do initial stage of looking through the data, and you will figure out those problems that I've mentioned, like signs on the back of the truck or things like that, things that are partially occluded, maybe, I don't know, various things. So you will update requirements here, and you will see probably how really the complicated problem is. So you'll probably see that certain things will need more attention, certain things will need more resources, and so forth. But then also, second thing is that on the results of prototyping, you will see that potentially we would probably use some more hardware assistance. We would probably use some depth information. We would probably use some IMU information and things like that. And then also the compute capabilities that you would need, you would probably have more understanding of those. And as soon as you have those points, you can start algorithm and hardware development in parallel. Basically, to a certain extent, those things can proceed independently, and then after a certain moment, you can do merging and testing on the actual device and so forth, and only then go to final product. So things that you will figure out during the prototyping stage potentially can result in a substantial additions to the project. So that is why we usually recommend to do prototyping for very complicated projects. Then computer vision as such is a pretty new area, and there are products where customer actually has to do something with the device or with the application that you provide to the customer to achieve the result. So potentially like panorama scanning or things like that. And designers usually understand computer vision things much better than customers do. So they understand the limitation of the algorithms. They think of this in one way, while customers usually do things absolutely differently. And one of the things that we recommend is that if you have a product that requires substantial intervention from the customer or substantial interaction with the customer, then you probably need to do some. You probably need to plan some testing prior to release, or actually testing at certain stage where you are able to correct the product itself. So you are able to do algorithm enhancements and maybe do some work that will be accepted. That will result in more customer acceptance, like updating documentations, maybe videos and all those kind of things, like tutorials that will show how to use your products and so forth. So in some cases you simply don't know how customer will react on your product, and maybe if you had that feeling, if you had that understanding in the very beginning, you probably would do some more extra actions. So we have one product, Itseez 3D application. This is basically application that allows you to scan person if you walk around the person. So you have to walk around the person and just point the scanner, which is simply an iPad with additional sensor on it. You have to point the scanner on the person. As soon as you've done first full circle, application shows you basically which parts of the model you scanned, and then you're all done. Basically, you can get and do some 3D model of yourself and so forth. So basically, we ended up in using occipital SDK for most of our parts. And first thing that we realized is that customers were unable to walk around the person all the times because of the space limitations, and maybe there was some, table, chair or something. So what they did is that they were scanning person, and then at certain moment they were putting device down, bypassing the obstacle, then putting it up and continuing scanning. So the whole thing was supposed to be working because of the SDK that was provided by the sensor and things like that. So it was supposed to detect like the points and everything, and then continue tracking. But that didn't fully work. So we had to go and re-implement the whole thing ourselves. And then there were other scenarios, like people were starting scanning from the legs and so forth, which gave us no idea that they are actually planning to scan the person. So we were expecting to see a face. And we worked a little bit on the UI enhancement, telling people that you should come closer, go back, and so forth. We worked a little bit on the videos, and then we got customer exception in the end. So currently we have about 300 scans per day, which was pretty unexpected number in the very beginning, I would say. Right now the number is even growing. So the point is you had to work on this user exception and user studies to understand what would be the potential problems, and potentially put some more algorithmic work to overcome this. And then maintenance of the vision products is actually a very specific aspect. Vision products as such heavily depend on an input. So what can happen is that after some time your product gets recalibrated, your product gets dirty, because it is outside. Some surveillance cameras can get dirty, shaken by the wind, point to different directions, lose focus, and so forth. So there might be some intentional tampering as well. So it would be always good for you to understand the potential problems and to be able to detect those potential problems, because otherwise you will have to do a lot of troubleshooting and customer interaction explaining why this didn't work like that. So it is always a good idea to spend some extra effort and put those things in the software to be able to check that you are actually receiving input that you are expecting. So we have a visitor counting software here. You see, this is basically people passing by, and then we are counting them. You see optics is getting pretty dirty in the time, so this is actual footage from it. But then there is another problem. So we are detecting too many people. See? This is what happens. People starting closing things and protecting themselves from us detecting visitors that are coming to the shop. And basically, as we figured out later on, initially the problem was that we were detecting too many visitors, but then there were too small amount of sales done, and basically shop owner wasn't too happy. So this is what was happening regularly. And our software detected that, and we were able to show that this is basically not the problem with the actual product. So as a conclusion, useful hits are here. Basically, do not consider requirements as final. Work for maintenance, ask for customers, and so forth. So all of those things might be very useful for you to look for. Okay, so we have some time for questions, I guess.
We do. Yury, thank you very much for your presentation. It was very useful tips and techniques and suggestions based on lots of vision designs that you've done today. Microphones are in both aisles over here. If you could queue up with your questions, and I'll start with one. You talked a lot about hardware in your presentation. So speaking of hardware, I'm curious to find out a little bit more about your company's involvement with both OpenCV and your accelerated CV product. The optimization work that's done on the latter, I'm curious to find out what, in a general sense at least, what sort of optimizations you do, and to what degree do you optimize? Yeah.
So our participation in OpenCV is basically that we are looking for purity of OpenCV. We are accepting merge requests from people who are willing to contribute to OpenCV. We are basically ensuring that things that they are contributing are not breaking things up. And we are gladly accepting new functionality. It's not that we are accepting only bug requests or anything like that. And this is open source project, so we are keeping the attention on that. But then also, our accelerated CV product is kind of closed source library that is companion to OpenCV, that allows you to take the library, take your OpenCV application, and then basically accelerate OpenCV application using accelerated CV, just simply by replacing one library call, OpenCV library call, with our call. And this is purely ARM optimized solution, so we don't concentrate on all platforms. We only concentrate on generic ARM Neon accelerations. And in a way, right now we are aiming for generic acceleration, so to say, so we don't kind of accelerate for a specific platform. It's the only requirement is that ARM Neon is supported by the SoC. So that's kind of the idea. And then potentially, of course, this could be even more improved if there is a need for improvement on a specific SoC, because there are always things that can be tuned.
Okay, great. I'm looking to see anybody at the mic. Otherwise, yes, there is. Go ahead.
Does your accelerated library plan to support like these mobile SoCs that are ARM but also have a GPU on the side? I feel like that would be really useful. There's a lot of mobile SoCs out there.
Yeah. So there is always discussion about this. I would say like ARM is now powering OpenCL things and so forth, which is pretty good performance. And we are discussing this, but one of the biggest problems is that not all functions are capable of running on OpenCL or on GPU without losing the performance, so to say. So it should be something big, something big enough that you can offload to the GPU. And essentially, what this limits you to is that you have your pipeline of the functions. You have a sequence of the functions, and some of them will be executed on SoC, and some of them will be executed on GPU. So you will have to do some clever memory management between those two to not to lose in the latency of the function execution.
So you're saying like the main barrier for you guys to like do your accelerated library on these mobile SoCs is that the memory management isn't is an obstacle. Is that what you're saying?
Well, it's not that it isn't possible. It's just that it is some sort of overhead that you have to properly work with. So you have to either implement zero copying or those kind of things that are supported. So zero copying, for example, is not supported currently on all SoCs, even that support OpenCL on ARM. So this is now pretty recent addition. So I think one of the things that will happen in the future is that we will have to implement this OpenCL support, but as I mentioned, only just for a selected set of functions that are worth actually starting. Because even not only the memory, but also if you have a function that you start on using OpenCL, then it should be pretty substantial function because there is an overhead on kernel starting and those kind of things. So if you have a, like, I don't know, 1/5 of millisecond function, then probably it doesn't worth it.
Thank you.
Okay, I think we're good. Thank you, Yury.
Thank you.
Thank you very much.